This section introduces two additional continuous probability distributions that are used in business decision making: the uniform distribution and the exponential distribution. The uniform distribution is sometimes referred to as the distribution of little information because the probability over any interval of the continuous random variable is the same as for any other interval of the same width. We can define the continuous uniform density function with the following equation, where a is the smallest value and b is the largest value, assumed by the uniform random variable. This slide illustrates two examples of uniform probability distributions with different a to b intervals. Note the height of the probability density function is the same for all values of x between a and b for a given distribution. The graph of the uniform distribution is a rectangle. Like the normal distribution, the uniform distribution can be further described by specifying the mean and the standard deviation. The mean mu is computed by taking the average of a and b. The standard deviation is computed by squaring the difference between a and b, dividing by 12, and taking the square root of the result. In this example, we are given a range for the uniform probability distribution. A is 3.0 and b is 6.0. Plugging these values into the equation for the mean and the standard deviation for a uniform probability distribution, we obtain a mean of 4.5 with a standard deviation of 0.866. Another continuous probability distribution frequently used in business situations is the exponential distribution. The exponential distribution is used to measure the time that elapses between two occurrences of an event, such as the time between hits on an internet homepage. The exponential distribution might also be used to describe the time between arrivals of customers at a bank teller drive-in window, or the time between failures of an electronic component. This equation shows the probability density function for the exponential distribution. Note, the parameter that defines the exponential distribution is lambda. You should recall from Chapter 5 that lambda is the mean value for the Poisson distribution. If the number of occurrences per time period is known to be a Poisson distributed with a mean of lambda, then the time between occurrence will be exponentially distributed with a mean time of 1 divided by lambda. It's simply the inverse of lambda. As with any continuous probability distribution, the probability that a value will fall within an interval is the area under the graph between the 2 points defining the interval. This equation is used to find the probability that a value will be equal to or less than a particular value for an exponential distribution. If we select a value for lambda, we can graph the exponential distribution by substituting different values for x into the previous equation. For instance, this figure shows the exponential density function for lambda equals 0.5, 1.0, 2.0, and lambda equals 3.0. For any exponential density function, as x increases, the function approaches 0. It can also be shown that the standard deviation of any exponential distribution is equal to the mean, 1 divided by lambda. Go ahead and open Excel file ATM fees and answer the following questions. Again, we'll produce a relative frequency histogram for these data using pivot table and a bar chart. Okay, now we'll find the mean using the average function, and we'll find the standard deviation using the stdev.s. Alright, so there's your mean and your standard deviation. And we'd also like to determine the probability that a randomly chosen bank's ATM fee would be greater than $3. So for this, we'll assume the distribution of ATM fees is exponentially distributed with the same mean as that of the sample. So we'll use expon.dist with x equal to $3, and our lambda is 1 divided by the 2.91, cumulative, true. And remember, in order to get that upper tail greater than 3, we need to do a 1 minus. So we see about a 35 to 36% chance or probability that a randomly chosen bank's ATM fee would be greater than $3.